Welcome everybody to the Flow seminar. For those of you attending for the first time, Flow stands for Federated Learning One Word Seminar, which was created to provide a global online forum for the dissemination of latest scientific research results in all aspects of federated learning, including but not limited to distributed optimization, learning algorithms, privacy, cryptography, personalization, and many more. So today it's my great pleasure to introduce you our speaker, Praneeth Vepakomma, who is a PhD student at MIT and also has a very rich industrial experience, including companies such as Meta, Apple, or Amazon. And today he's going to tell us more about split learning and its recent theoretical advances to ensure privacy. So thank you, Praneeth, again for agreeing to give a talk, and looking forward to your presentation. Please, the stage is yours.
Sure. Yeah. Thanks, Samuel. I actually really follow this series very keenly, and at the least make sure I at least read the talk announcements. I find this a really nice audience in general. Yeah. So my talk is mostly going to be on the split learning variants, more on like an engineering perspective, and then some theoretical work towards its privacy. So this slide will not need as much of time, but this is just a context setting slide. We're interested in, just like you're interested in all sorts of topologies and questions about how to incentivize and how to deal with privacy and resource efficiency. The same questions fall on into split learning for federated learning and distributed and privacy preserving computation in general. So that's the federated learning slide. I'm sure you've seen it many, many times. So I'll let you just stare at it and not say anything except that you average weights, and the weights is what are shared from clients to servers during the training process. Okay, so now given that we're in the FL seminar, let's move to the newer topic, right? The split learning. So this is a variant of federated learning, in my opinion. And when we introduced it, we were concerned about how we could make distributed ML more resource efficient in the extreme case where the clients are very resource constrained, like today's edge devices, for example. That said, one way we could do that, it was through split learning, but split learning ended up becoming a sort of a small paradigm in itself over the last couple of years. But that said, I still think that the landscape is still open. There could be something other than FL and SL. There's been some talk around local parallelism, and there's been some papers around it. So there is still room in here. So we don't need to fix ourselves within either of these silos. There may be more room in terms of the high-level landscape. So within split learning, what happens is every client so basically the whole network itself is split. So that's the split learning. And most of my initial slides would be pictorial. So I want to keep it high level to start with before we get into the more nitty-gritty aspects. So the whole model itself is split, and part of the model is shared with the client. The rest of the model, say in this case, after the split layer, the rest of the upper layers are with the server. Now, the forward propagation, the communication that gets shared is just the activations from the split layer. So only one layer of activations. I want to make sure it's not confused with activations from all layers. So there's one layer worth of activations that go to the server during the forward prop, and then you have a traditional back prop and one layer worth of gradients that go from this split layer in order for the next layer to continue the back prop. So this by itself is split learning, but of course, just like in federated learning, although the earlier slide was a simple slide, there's so many interesting questions. And there's so much room for improvement and so many variants of FL and SL that would come into play when we consider practical issues. So one issue, for example, is the finer detail that you don't see in this slide, which is if each client is using the shared resource of the server's part of the model, how does it not end up, creating 100 models if you have 100 different clients where the server's part of the model is flip-flopping from serving one client to the other, right? So that's not good. So how do you see convergence to kick in? So So that's where the most vanilla version of split learning, which is called as sequential split learning, comes in. This is the finer detail of what happens in the previous slide. In sequential split learning, this is not the recommended version. I would recommend anything above the parallel, but it's good to start with sequential for the talk. So in the sequential version, what is really happening is clients get a chance to partake its learning with the server one at a time in sequence. So that's not practical. But at least the client, I mean, at least the convergence happens here because the client, after, say, the client one, after it partakes with the server, it would share its local weights to the client two. And then the client two partakes with the same server, and these weights are the same weights. So you don't have to copy the weights, you have the common set of weights. But there's local weight sharing between clients. This is one way to get the model to converge. But that's not at all practical, right? So, but this is what we thought about when we thought of split learning in the very beginning. And then we quickly had many variants crop up, right? So the next version that is parallel split learning, which is also implemented in a few startups now, is as follows. So all the clients kick off asynchronously whenever they start their training. And then they pass their activations to the server, just like so far. The server continues the forward propagation. And then what it does is it notes down individual client losses. Okay, so you just, the server is measuring client losses individually, and taking a note of it. And then the server averages up all the client losses. Certainly there is some synchronization issue with the server waiting on for the average. Similar to, there is a similar synchronization issue in federated learning as well. And we'll get to the finer details, but in here, the initiation of the clients and not having to communicate between any clients, and also the clients, kind of working in parallel at whatever their speeds are with respect to the resources is achieved. And instead of the copying the weights, the averaging of the model losses is what being done, and the backprop then happens to minimize the average of the client losses as opposed to individual losses. Okay, so that's that. So what else has happened in this space, right? So there's some more, well, there's federated averaging. One of the federated learning algorithms. There are many more recent federated learning algorithms in that paradigm. And then there's local parallel training, which has been some inspirational or motivational setup for people in distributed ML in general. This is a recent setup. So in here, what is happening is, in distinction to split and federated, if you see in split, the entire epoch is being split. The epoch is split across the client and server. So the cycle is split. In federated, the entire cycle is with the client, the epoch cycle, in the traditional settings. But in here, this is kind of a hybrid in the sense that there's some cycle that happens just on the client, and then some cycles that happen with the server, right? And then, of course, there's the notion of how do you resolve problems of the client cycles diverging and not being in sync with the server cycles, and do they operate all the time, or is there like a lag? Do you pause in? These questions come up, and these are very valid questions, which will be the guiding principles for the other variants that keep coming up as we go along this talk. Okay. And then there's been a split federated learning, which is a hybrid between SL and FL. And then here there is a local averaging. Basically, there's a federated averaging of the local weights of the clients as opposed to the entire network. And then the rest is the split part. And then typically you could run this, think of this as like parallel SL plus federated averaging, because sequential is just like a textbook case, unless there's a very unique reason for why someone would like to do that. And what else? What else is happening as we are building upon these details, right? So let's keep moving along. Are there any questions? Just the initial setups. And you can feel free to interrupt me in the middle. I'll also keep asking once in a while. Okay.
Yeah, so I would maybe just one quick clarification question in here. So is it the case that for SFL, so the bottom left corner of your slide, that that would converge to exactly the same solution of Fed averaging would converge to? The only difference is that how you do the computation?
In principle, yes, but we've not done any convergence bounds connecting
Okay.
one to the other, or even within split learning. I think I only know one workshop paper within one variant of split learning, not even split fed, that has done some convergence bounds using standard assumptions like Lipschitzness and stuff, but not like really advanced stuff. So, but in principle, yes. It would be the
Okay.
same case even in sequential SL, if you think in principle, because the client one is passing its client weights to the next client. So it's just the hardware device that is running the things is changing. It's the same weights that is continuing with. So this would be traditional learning as well in that sense, even with the traditional deep network,
Okay.
regardless of federated. There's no averaging either, for example. The
Mhm.
averaging starts kicking in here, so maybe there's some more that kind of similarities.
Okay. And just for parallel split learning, do you propagate, just so I understood it correctly, do you, so you say like you propagate the average loss? So it means like you don't finish kind of on a client, don't finish computation for a client one or client two, but you kind of propagate the exactly the same thing to both of them?
Yeah, so you finish, just to be sure we got it right. So you finish the
Mm-hmm.
forward props of two clients,
Mm-hmm.
and
Okay.
then you have two losses. You average the loss,
Mm-hmm.
and then you back prop once till the common split
Oh, okay.
layer, and then
Mm-hmm.
you back prop accordingly. And then the clients could end up back propping in a slightly different way because they were trained on
Yeah.
different data sets.
But they originally received the same, or like the
Yes,
same
yes,
states, right? All right.
yes. The
Great.
initial
Got
is
it.
exactly the same. Yeah,
Yeah. Thank you.
great. Cool. Okay, so moving along, a similar kind of a thought process. So kind of evolution using sequential is in parallel, and then there's more finer details and tweaks and tricks that started happening, which are, I'm just putting it under the SL variance bucket, and this is wide open. There's so many things that are possible. At some point, it gets confusing to me, and this is philosophically speaking, of what is a tweak that is just a tweak that is being borrowed from traditional ML literature, traditional deep learning literature, versus what is a tweak that has been borrowed with more backing for some distributed machine learning reasons. So that's the reason the variance bucket is really wide open at this point. For example, if there's a lot of traditional ML literature about compression weights or gradient sparsification. The same thing could be borrowed in here, but at the same point, there could be something more intricate that has not been seen before. That is maybe a subtle difference that can be done within the variant bucket. Okay, so we've seen these two. Now there is another version, for example, that is the cut mix SL, and basically it's kind of motivated by a lot of literature on what is known as mix-up, which is kind of some sort of linear interpolation or interpolation in the encoded space, or like in the representation space, in the activation space. These have been called with different names: manifold mix-up, latent space interpolation for variational autoencoders, and so on and so forth. So what we do is we are borrowing from how we're kind of inspired by how we can further reduce the communication payload when you do this transfer of the activation from the split layer. So what we do is we kind of put in a mask, a binary mask, which is basically sparsifying which of the cells in the activation are going to be considered from each client. Okay, and there's some mixing ratio. So you sparsify the activations of the client in blue at the split layer for the same layer, or whatever the split layer is for the client two, you sparsify the activations. And we then do a mix up, some sort of a linear combination of these activation space that has been sparsified. So now you're sending much lesser bits. So this is kind of a cartoon representation. You pick whatever your mix-up ratio is, and you sparsify. So this is now, instead of the entire split activation, you sparsified it, and you got the rest of it from here. You mix that up, you get the mixed up activation. So this potentially, again, only intuitively speaking, could not just for definitely for communication. You can just see it. There's a communication benefit, but intuitively speaking, it could also potentially have two other benefits. One is for privacy, as long as we can ensure that this mixer block is privatized formally, then it would help for that. So there's a DP version of this that is the most recent work we've been doing. And then third application, now this is a bit hand wavy, actually a lot hand wavy, which is could still help with some sort of non-homogeneous settings, because they're trying to find a common space to work with. But non-homogeneous ML in general is a very wide space to talk about this. So much going on there. So that's why I'm hand-wavy on that. But definitely for privacy. Okay. So some of the guiding principles of what we've seen in the variants, right? So there is some sort of a update imbalance problem or issue in general between servers and clients. It's something that needs to be taken into consideration when you design a variant. You don't want to have a client go on its own path and server go on its own path. You want to have some sort of a convergence as you design these kind of updates that you've seen before. There could be a client model detachment issue as well, where the client is totally off and the server is doing something else. And there's a privacy problem. That's a huge problem in itself to work. Problem space within split learning. Quite an open bucket. Super early. I would say there's more work on these variants that has happened more actively. The privacy space in SL is like even more early of where things are. I guess I would also add in the optimization, studying with more rigorous optimization principles from that viewpoint. For split learning has not been done as much as has been done with traditional SGD and Atom and FL in general, all the versions of FL. So that's an open space too. Okay, so moving along, this is a variant we are more excited about for the efficiency reasons. There's no privacy version of this. And after this, we would go towards some privacy parts of the talk for regards to split learning and some early versions of it. Okay, so in this ADA split version, so this is just FL and SL, so let's focus in here. So there's a few things that we do here. One thing, this is more inspired by the local parallelism approach of distributed ML, where you can have a local client cycle. So what's happening here is a client has a full complete cycle in itself. So every client can compute a local client loss on its own premise. And there may be a basic question that might crop up. If the whole network is ending here, how would the client end up getting a loss somewhere early on? What we literally do is we just add up a softmax layer, a final layer here itself, so that you just convert it into a classification probability and you can evaluate the loss. We do that here. So now we have a local client loss and there's no communication with the server yet. At the same time, there is like the local parallelism slide, there is some global updates which happen at a much slower frequency. So they don't happen as frequently as the local updates happen. So think of it like if you had 100 epoch training, think of maybe, I'm just making some extreme examples. Say you do 80 epochs of just local training on the clients. There's no sharing at all, nothing distributed yet. And that's when the global training kicks in from the 80th epoch, and you have only 20 more epochs of server. So you're reducing communication as long as you're training a model that works reasonably fine. And then there's the global update that kicks up. The other thing is, again, borrowing from the general FL literature, which is we don't, for more practical reasons, we don't have to train with all clients all the time when we're participating in engaging with the server. The part where you're doing the global updates, we don't have to do that all the time. So there are different strategies one can use. One can use to select a subset of clients. The strategy we've exactly used in our code, and the code is completely open to share, is the upper confidence bound. So we look at the upper confidence bound of the individual client classes and we select, and it's like an explore exploit trade-off of when the client would like to use the server's computation power or learning power, not just computation, but learning power in general. So there's a subset part, so that is there. And then what is the other? Yeah, the final other. So there are two more important things. The thing that I find more exciting is when the global updates happen, it's a bit different from the split learning you've seen so far in the previous slides. The global updates happen in a way that they take the output of the client from the split layer. They start with that to continue the forward, and then they reach the full forward. Everything's same so far. Now, when they do the backprop, they just backprop until the server's split layer. They never send back the gradients back to the client. So there's no gradient communication ever between the server back to the client in this setting. And the only intuitive reason for why this is not detaching into two separate models is because the client is feeding its input to the server. and that is changing whenever it does. That's the only thing that is influencing how the server shared resource is learning its backdrop. Yeah, and then there is an averaging of losses as well when the server is trying to backdrop. Averaging of the client losses and the server's loss. Okay, so these are the things. Oh, there's one other thing. This is the sparse update. So this is, I think the sparse update is a much internal tweak than the main things that I said, which are these three things. The sparse update is basically, you can start trying to, so I mean, this has purely helped only for empirical reasons. So there's no magical reason I can cook about the sparse update. But it certainly helps us for our training performance when we basically sparsify the client's outputs. So there are masks that every client can have a different mask that you use to sparsify the outputs. And that is somehow helping the training. It will be, I'm very sure there's some sort of principled way of some trade-off that is happening in here, which is worth studying, but I don't want to speculate on it. I just want to share what the steps are. Okay, so that's the ADA split. Let's see how ADA split is doing. Any questions here?
Yeah, maybe if you can comment, please, on this intuition that actually like you don't have like these detached models. Is that something I'm a bit missing? Like how is that those kind of like the base model that you have on the client and then the end model, like they are somehow aligned with, since you actually, if I got it correctly, you never actually communicate anything back from the server. The communication only happens from the client to the server, right? Never back. Okay.
Exactly. Never back.
So how's how? Yeah. So kind of like where's the feedback for the client?
Yeah. So the feedback is in two ways. The way the client is influencing the server is the final loss that is computed here includes the performance of all client losses, at least the ones that are participating in the subset, and also the server's loss. That is one loop. The other can be viewed as some sort of, think of like an extreme case, which is say pre-training, for example, or like some frozen weights. Pre-training still helps the learning process, as opposed to no pre-training, for example. And then after pre-training, these are frozen, and literally the server only works here. So this is like a modified pre-processed pre-training of the inputs into some other activations that the server is beginning to take up, while still following standard things like batches and training and testing. Those are the two things that I see. Yeah.
Okay. Yeah. So do you think that like, yeah, so if you do actually like a full pre-training, meaning that locally, like on those clients, you obtain the best model with respect to this client loss, so to the softmax after the split layer, then you can actually like, you would never update any more the weights, right?
In the extreme case.
Correct? Okay. Yeah.
In the extreme case. But this may not have enough capacity to get there, but that's what it is. Yeah. Okay.
Thank you.
Yeah, and then the fact where the sparse updates were empirically helping us or surprising us was when we were testing with non-IID. I mean, non-IIDs of many kinds. So label non-IID. So the labels are different across classes. Inhomogeneity caused due to labels being different across clients. So when we tested on mixed CFAR, like mix up of these kind of data sets, the traditional data sets, the sparse updates were helping ADA split perform better in these kind of non-IID settings. And that's the reason I feel there may be some principled way of studying it, whether it's empirical or theoretical, of what is helping, why the sparse updates, in addition to this setup, is helping in the non-IID setting. So again, I can speculate. I don't want to speculate too much, but at least to not just leave it there, I would conclude on my speculative side saying that the sparsification could potentially help the clients click up together into samples that are somewhat more homogeneous or or has more transfer learning, the transfer of knowledge that is going to benefit them for the overall training. So that could potentially be the reason why having a different mask on what each client is communicating, so it's not the same mask, could potentially help. Okay. So yeah, so I think yeah, tables are nicer. So yeah, so ADA split under some of these choices of where you cut and how frequently you communicate with the server, things like that. Under some setups, we do see with these non-IID, at least the created non-IID popular data sets that we create, that it performs much better than other split versions for sure. But also, it's good to comment that there are a lot of variants within federated learning, given that federated learning is very popular. So within some of the recent variants that we tested with, Fed procs, for example, does as well or sometimes even better or equally well, on these data sets. Like for example, here it's like above, at least the mean is above, but it's some plus or minus. So you cannot significantly say they're different, but sometimes pretty good. And also Fed procs seems to be doing well, regardless on the communication bandwidth as well, consistently over split learning. There could be some cases where data split is much worse. I will comment on why this could be happening with data split or split learning in general, because the talk has been about split learning being communication efficient all the time. That is not the case. So I'll comment on this after I finish this table. And the bigger benefit in terms of Fed procs we see with ADA split is on the compute resource. This is for more trivial reasons because split nature of the things, of number of operations, and it gets pushed even nicer because because server and client are operating separately. So there's this. So the thing I wanted to comment about the communication aspect is let's stare at just the FL and the SL thing, right? So in FL, although the payload is much heavier than SL, what is being communicated in terms of memory, because the entire model, which is true, but the communication is much less frequent than in SL. In FL, the whole training is done, all the rounds, so all the epochs, and then per round you send it up after whatever your batch of training epochs are done. In here, you have to send the payload, which is much smaller, but you send it more frequently up and down. Every epoch you send it up and down in traditional SL. And we see something of that sort is happening depending on the communication update frequency. When it is getting closer to the traditional parallel SL, which is not as much as local training at that point, local parallelism, that's when we see sometimes FL could do better in the communication bandwidth. It also depends on other factors, other independent variables, but this is some intuition. Okay, so that's that. So we've seen mix up. I'm kind of, let's see, any questions? Also very on time. Okay, good on time.
Yeah, we good on time.
Yeah. Okay.
Yes. Maybe just about if I can ask a quick question here about the mixer, actually, because you had that slide before as well. So what I was wondering, like when you do the mixing, is it the case that you consider that as like after the mixing, that you consider that mixed smashed data as a single data point? Like, do you understand what I mean? Like that you actually you kind of like join, like let's say you have a data point one from client one and data point two from to client two. Now you smash them together. So do you consider that as actually as an activation that came from a single client for the the rest of the forward propagation?
Yeah, that's exactly how I see it. Unless there is a alternate way of looking at it, which I not thought about, but that's exactly how we see it. Yeah.
Okay. Yeah. Thank you.
Yeah. So kind of switching gears towards some early thoughts around privacy within some of these variants for SL, right? So yeah, so one thing that we were able to hunchback on is mix-up queries in general are simple queries, and DP DP mechanisms are easier to come up with for simpler queries relatively, as opposed to for the entire neural network, which is a big bottleneck. to design for split learning. And also for split learning, typically the weights are what need to be privatized. But if you want to, if your communication involves activations, that's a very hard problem. It's more like local DP or like instance-wise encoding. So it makes these are other reasons which make applying DP for split learning a little tricky. As far as wherever activations are concerned, for the weights you could use traditional mechanisms for DP that have been and are being developed for FL or any deep learning in general. So the part that helps us with the mixer strategy is we could consider the mixer itself as the query that needs to be privatized, and mixers are very simple queries. There's some sampling involved and there's some linear combinations basically. So that's a much simpler query to think about. And people have thought about differentially private mixing in general, because mixing itself is a thing these days in the ML world. There's a NeurIPS workshop on just mix-up. I was surprised to see that on the December 3rd. So people have studied mix-up a lot for different perspectives. And for that reason, privacy mechanisms, DP mechanisms for just mix-up queries have been studied in like ISIT kind of literature. So we were able to borrow that and see what we can do within cut mix based, this mix-up based SL basically. And other things that we borrow in the mechanism is this lot of work in the landscape of DP on what is known as privacy amplification. There are many ways to amplify the privacy utility trade-off that you get by doing some pre-processing operations. And one of them is subsampling the clients. And if you can do that, that would help your privacy budget. And then the notion of privacy we use here is RenUDP, which is basically saying if you have neighboring data sets, how much is the RenU divergence upper bounded by between the outputs of the queries applied on these neighboring data sets. So that upper bound is the epsilon basically. So is the RenU divergence less than or equal to epsilon, then it's epsilon RenUDP. And there's a translation to go from RenUDP to classic approximate DP, epsilon delta DP as well. And within RenUDP, RenU divergence, there are many kinds of RenU divergence. So there's an alpha parameter that decides what kind of RenU divergence you're playing with. So I would recommend looking at this work. We are submitting a longer version to a journal, so that should be out soon as well, in a few weeks. At least I see the final polishing is happening right now. But there is one of this version is in the workshops in Europe as well, the shorter version of how to do DP queries for a cut mix in this kind of stuff. Yeah, so this is typically the kind of bounds you see. You could mix up at the input data and get RenUDP query of that, or RenUDP version of that query. You could mix up at the cut layer, at the split layer, and you can do the passing that we were doing with the patches, and you could get that kind of query. And you could get a vanilla version where you're just sending noise added to the activations to get an DP. And the ordering is kind of reasonable in what we would expect. So the RenUDP, the epsilon you get for the cut mix version is better than the raw data version is better than just vanilla split learning, for example, which is not good at all actually, but at least the order is that way. And you would see what these epsilons look like in the details in our paper, but we do make some assumptions on some sort of boundedness of especially the data coming from the split layer. Which is something that needs to be studied more carefully on how that will be controlled for in practical settings, not just during training, but during testing as well, for example, apart from doing things like force normalization or flipping of some sort, which could be one option. But also we need to think about the attack model and what it means in that setting, and this is reasonable, things like that. Okay, so that's that, and we've done some. There's more work being done on the utility privacy trade-offs for this setup. So what I want to do is I want to take a step back and see if there's a simpler version of the question of sharing activations with privacy as opposed to weights with privacy. And one of the simplest versions would be, one simple version would be like thinking of just linear neural networks with limited capacity Another version of that, another simpler query of activation sharing that usually happens is what you see with things like PSME and stuff, where people visualize the final layer or the embedding layers, and where we could think of the embedding query or like the manifold embedding or the manifold learning query itself as a query that could be privatized, and how could that be done in an efficient way? So this work is a AAA work on how coming up with a supervised way to embed the data that you have in a way that is okay with train and test, the rules of train and test testing that you need to follow. So it's supervised in a really proper supervised sense. But at the same time, the main contribution is how do you privatize this query? So the query ends up being an iterative update of this form. The good thing is the only terms that access the raw data is the graph Laplacian that is computed here. That's kind of understanding the neighborhood structure of the data. This is the DAG version, but the same thing, and then the graph Laplacian with respect to y, and then there's the raw data itself. Well, this is the initialization, it's not raw data. So this could be totally random initialization. The raw data is based on principal Laplacian. If we were to do a privacy mechanism for these kind of things, if it was iterative, I mean, typically you would have to do some randomization or noising after every epoch, after every iteration. But in here, we can get away with it through post-processing by doing the follows, which is we only run one iteration of it. We make it differentially private. We show how we do that. Only one iteration is made differentially private, and then we consider that as our new data set, new X, and then we recompute the LX. Instead of computing LX with respect to the raw data, in the next phase, we compute LX with respect to X1, which is what has happened after the first iteration has been run. At that point, post-processing kicks in, and there's no other access to raw data, so you have differential privacy all through until you get the embedding that you care about. So we've done this. This the definition of differential privacy that you might have seen many times, the classic version of the approximate differential privacy. And the question boils down to, if you did a classic Gaussian noise mechanism, what is the global sensitivity of this query, basically, of one iteration of this query, so that we can calibrate noise in proportion to the global sensitivity, and then you have DP guarantees. That's how the proof typically works, the classical proof works. So the main work goes into how do you derive the global sensitivity of this query. Just for audience who are not like DP of a DP background, global sensitivity is just measuring with respect to some choice of norm, what is the maximum difference of within that norm of the outputs of your queries when their queries are applied on neighboring data sets, where again the choice of neighboring is again defined based on your choice of norm. Typically, the neighboring is being very often defined using the Hadamard distance. Sorry, the Hamming distance. But you can always change the input metric to something else, and that's called metric DP. You could do the same with the output metric with which you're measuring the difference, which is also part of metric DP. So we design a bound on the global sensitivity, and now we know how much noise to add, basically. That makes it DP, the first iteration. And then you see these kind of visualizations like that you saw here. This is I forget which data set, but yeah, this is color coded by class labels. So there is some separation that you can see post this embedding. So we could still do some analysis or analytics on top of these embeddings that have come out of the neural network. But there's a simpler version of how to privatize activations. It's not for the entire network, right? So we also make use of some public data set if you're trying to do some more intricate tasks like matching, but matching is typically not, although we show it, matching and querying, like information retrieval, is not typically a DP style query, because DP is all about, think about fraud detection in the extreme case. DP is all about, so in the extreme case, you are identifying someone as fraud, you are identifying a record. So the same thing with matching. If you're trying to match with respect to a query and retrieve results, you don't want to match something that is exactly the same as the query, because then the query is out. So the main, so that's the blessing and the curse. So you could do simpler tasks, but if you want to do more complex tasks, then the DP is not the right setting if you're using these activations in some form. Okay, so I have another maybe 5 minutes of content. So yeah, so there are other variants of split learning. So there's this boomerang or like U-shaped topology where both the raw data and the labels can be hosted on the same client. And there are two cuts now. So 2 times you're splitting the network. So the front and back layers are with the client, only the middle layers are with the server. This is an interesting setting. It makes sense, for example, in healthcare, where labels themselves are highly sensitive, potentially having the information of what the diagnostic is for the person, for example, as opposed to just the signals of what's in their record. So how do you, and this is certainly not formally private, it's a good start, just like FL, where there's no raw data sharing or raw label sharing in this setup as well. But how do you make it private? So that comes, there comes the question of label privacy. This was considered by, this is not our work, but this definitely is motivating a lot of our work now, which is coming from the ByteDance, the TikTok company, within the context of split learning. But label privacy here is not considering features and labels as sensitive. It only considers the labels as sensitive, and features are considered public. If both are sensitive, it's much more tricky problem. Yeah, and there could be some sort of potential no-lunch theorem that might happen there. But in the case where features are public, apparently this setting with only labels being sensitive is pretty reasonable in some very large companies, large tech companies. And since it's a recorded talk, I don't want to go into exact use cases, but the setting has practical implications of being reasonable. So this is in here, they do a version of randomized response, basically, where they compute gradients with respect to the zero loss, with the zero label, loss with respect to the zero label, and the same with respect to the one label. And then they do, they pick a sample and they interpolate between these two gradients. And that's how they're obfuscating the gradient between the zero loss and the one loss, depending on U that you can pick from, some pre-specified distributions with specific variances. And once you can privatize gradients, this is super useful because you only need to backprop with respect to the label, and label only plays a role when you compute the loss and start beginning your backprop process with respect to the loss. And so just doing chain rule, you can use this grad perturb mechanism for the corresponding partial derivatives that have to do with labels, basically. So those parts are backpropped, are perturbed. And that's how these guys ensure label privacy within split learning from formal privacy settings. So it's DP in here. So now there's other possibilities, and no one has thought about privacy or other implications, but split learning would work in the vertical partition setting in general. There are other questions like non-ID, what happens, and what to do, how to do privacy in here. So this is just creativity. There's no, you can build up whatever block you want here. So I don't want to comment too much on this, but this is an open area of thought as well. Okay, so briefly, the other approach is post hoc privacy, where the question is, there's a lot of works that do some sort of informal empirical reconstruction attack prevention, and then they call it as privacy, but this is kind of heuristic. No one knows if it's really formally private or not, because there's no worst case guarantees. So for example, one of our approaches in CVPR is this heuristic approach, and this is not formally private. What we do is we learn a network where we learn a pruner that tries to prune the activations in a setup where it's trying to prevent the reconstruction of the raw image of the raw input data. At the same time, we are also trying to predict a specific attribute of interest. So maybe, for example, what is the age of the person? We're looking at faces, but you want to prevent reconstruction of the entire face, for example. Empirically, it shows some interesting value, and there's many papers of this sort, not just from our group, like all over the place. There's too many papers of this sort that are happening, but there's no formal guarantee. So is there something that we could do in this setting where we take these existing techniques like the one I showed or the other ones that exist with informal privacy, and as a result of that output during the inference stage, do something so that now you can guarantee formal differential privacy? And the something is all about how much noise to add or how much randomization to create. So what we do is we borrow from a metric DP because there's some impossibility results of not being able to do the standard DP with instance encoding, where you're doing privacy per instance. after the training for inference case. It's not training data privacy, it's inference data privacy, and that's not doable because you don't know, nothing is bounded there. So you don't know how we could get a worst case guarantee. There's an imperfect result. But that can be, you can overcome it if you do metric DP, where instead of doing Hamming metric for your choice of neighborhood of data sets, you could do a different metric, and you can have a different metric with output as well. So the input data sets are restricted within a separate metric, and so that's what the output would be. So the question here is how much noise to add, and how do you calibrate that? So there's this wonderful work called Proposed Test Release by Sequential et al. It says if you do not know the global sensitivity, or if it's very hard to calculate, you don't know how much noise to add, but there's something called the local sensitivity, which is specific to how sensitive the output of the query is for at a given data point, as opposed to for all possible data points, which is what is needed for DP. But then if you add noise with respect to local sensitivity, if you could compute that, it's not guaranteed that it is DP all the time. So how would you propose a local sensitivity and then ask the algorithm to test for it, whether the local sensitivity is enough of a computation, enough of a calibration, so that if you add noise with respect to that, you would be able to release and have DP for sure. If not, it will say you cannot return anything. Like what you're proposing would not ensure enough noise that you get DP. So this is the proposed test release mechanism. So now comes the question of what is the local sensitivity of a deep neural network? And that's kind of tricky to compute. It boils down to being upper bounded by the local Lipschitz constant of a deep neural network. Now, so that could be a potential proposal because we don't even know analytical form for local sensitivity for deep neural network, not just global sensitivity. So we could start with the local Lipschitz constant. But there's recent NeurIPS work that shows that for ReLU-based networks, you can exactly compute the local Lipschitz constant. But it blows up in compute and basically computational resources if it's a very deep neural network, but for some blocks, it's still okay. That's the caveat there. So basically, we start to modify the proposed test release algorithm, where we start our proposal based on the local Lipschitz constant. And then there is some other gates that we need to fix so that the PTR algorithm itself, the testing algorithm itself, is differentially private, because you don't want to do anything during the testing that is breaking the differential privacy in order to decide whether the noise is good enough or not. And so that's the modified version of PTR. And there's only one open parameter that we've introduced here, which is the choice of neighborhood, because we've changed the metric to beyond Hamming distance being less than 1 or something to any metric with some metric neighborhood of less than or equal to R. So the R parameter needs to be figured out, because for different R parameters, you have different definitions of DP, metric DP, that are not equivalent or comparable. So you have different versions. So the question is, how do you choose this R? And what are the implications of choosing R on the privacy utility trade-off? So we've studied that as well. And you could typically think of this as a search algorithm optimization, like a golden section search or some search where you're trying to find a minimum or maximum of like a unimodal thing. If you had an oracle function, you could use that. We could do that kind of search to start with some R and borrow down. So it's kind of like binary search, but for finding the minimum maximum. You could do that. And we also study the effect of the choice of R on the privacy trade-off in the paper. Yeah, so I'd like to conclude there on thoughts and even more recent work. The variants themselves are recent work, but the privacy is like even more recent work of where things are heading towards.